Hello, hi everyone, welcome back to the series. Continuing in this binary search series, we'll be solving this problem of factory machines, which is yet another interesting problem and a very beginner friendly problem to brush up the concept of binary search. So, let's read the problem statement. We have a factory which has n machines installed in it, which can be used to make products, and our goal is to make a total of t products. So t is given in the problem statement, the number of products which I want to make. Now for each machine, we know the number of seconds it takes to make a single product. The machines can work simultaneously. So let's say if we have n machines, then they can work simultaneously. Okay, and we can freely decide their schedule. What is the shortest time needed to make t products? So we want to make exactly t products, and we want the shortest time needed to make the t products. So that's the problem statement. The answer is basically the time. So again, try to match with the pattern which I explained in the very first video of binary search, that is like minimize something such that this or maximize something such that this. Does the problem satisfies that kind of pattern? Yes, we have to find the minimum time such that the machines can make t products, and we have n such machines. So whenever you find something like this, try to think about binary search. So in the input will be given two integers n and t representing the number of machines and products. The next line has n integers representing the time needed to make a product for each machine, and there are n machines we know. So in the output we just have to output one integer representing the minimum time to make t products. Fine, the number of machines can be 2 into 10 raised to the power 5, while the integer t goes up to 10 raised to the power 9, and k also goes up to 10 raised to the power 9. That is the time taken by each machine to create a product. Let's better understand the problem statement and take few observations using an example. Okay, so let's take this example. We have three machines and we want to create seven products. Okay, the first machine takes 3 seconds to create the product. Okay, let's see, it's seconds. Yeah, it's seconds. It takes 3 seconds to make the product, while the second machine takes 2 seconds, and the third machine takes 7 seconds. Now, what I want is the minimum time. Okay, so we want to find the minimum time such that the machines can make t products. Okay, now how can we solve this problem? Obviously it's a binary search problem, and it's a binary search on answer. So what is the answer? The answer is basically the time. Okay, so let's represent time by variable t, capital T, or let's say we have answer. So this answer represents the time. Okay, let's say we take x time. Now let's observe the monotonicity in the behavior of answer. Let's say we take x time to make these products, to make these seven products using these machines simultaneously. Obviously we have, if we have three machines, we'll be using all of them simultaneously, because that's the most optimal way. We want to use as many machines as possible to create our products. Okay, so that's obvious that we will be using all of the n machines and put them to the work. Now let's say we have, let's say the answer is x, that is we take x minutes or x seconds to create t products. Now if we can create t products using x seconds, then I can also create these products using x plus 1 seconds. I can create these products in x plus 2 seconds. I can create these products in x plus 3 seconds, and so on. All of them are valid answers. While on the other way, I cannot create these t products in x minus 1 seconds. I cannot create these t products in x minus 2 seconds, and so on. So these are bad times. You see, bad. Why? Because we can't create t products in these time intervals, while these are good elements or good times where we can produce t products, okay, using these machines. Now, what is the target in this problem is to find this x, because this is the shortest time where I can produce my t products. Fine. So very similar pattern, the familiar pattern, if you have followed the playlist from the starting. Obviously this problem is very easy to implement for you. So what do we have to do is to just we have the search space for answer, so we have to define the search space for what would be the search space for the answer. Obviously when we have no product, we don't take any time to produce that, and in that case the answer would be 0. While on the other hand, we may go up to a very large number. The number of products may go up to 10 raised to the power 9, while the time taken for each product may go up to 10 raised to the power 9. So in case we have, let's say the n goes up to, the limit for n is 10 raised to the power 5. Now in case we have n such products, like 10 raised to the power 5 products, where the timing for each of it is 10 raised to the power 9. That is, each machine takes 10 raised to the power 9 seconds to create each of the n products, and we have 10 raised to the power 5 products. So it would take me 10 raised to the power 9 multiplied by 10 raised to the power 5, that is 10 raised to the power 14 seconds to create n products. To create n products, I would take 10 raised to the power 14 seconds. Let's take an upper limit of 10 raised to the power 18. So I'm sure that my answer will not exceed 10 raised to the power 18, even in the worst situations. The worst situation is when all of them are at its extreme, like this. Even in that case, the answer won't exceed this number. So the right hand side is 10 raised to the power 18. Now this will not fit in an usual int type data. Int type, it has to be, so we have to declare, we have to use long while implementing this solution. We have to use long in C++. Fine. Now let's come back to the problem. We have our search space, we have our answer. Okay, so this is the search space for this answer. Now we want to perform the binary search. Okay, now we know the procedure for binary search. Find the middle element, that is guess the mid. So in this way, guess the mid. Now this is the time which I am guessing that, okay, this can be the possible minimum time such that machines can make t products. Okay, now let's see if it is valid or not. How do we check that? That is the main challenge. That's how we check if we can make t products in this interval of time. Basically the definition of the Boolean function which we use in the binary search. Okay, so how can we check that? Since I want to make t products, what I would do, now observe that all of the machines work simultaneously. So the first machine has the interval to produce the product for first machine is 3 seconds. So if the first machine creates a product in 3 seconds, then in mid seconds, the number of products that the first machine will create will be mid divided by 3. Similarly, the number of products that the second machine will create in mid seconds would be mid divided by the number of seconds which this machine takes to create a single product, that is 2. In the same fashion, mid divided by 7 would be the number of products which the third machine will create in mid seconds. So if I sum all these values, if I add them up, what is this going to give me? It is going to give me the number of products. And I have counted the number of products which I can create in this guessed answer. Now compare these number of products with the products which I want to create, which is T. So if these products are greater than T, that means this is a valid answer. This integer mid lies in this range here. It is a good integer, or it is a good answer. Fine, because I can create my T products in this time. Fine, so I will store mid into my answer variable. Now is this the final answer? No, I'm saying this mid is present in this range, in this on this good side, but I want the first one, that is this X. So I have to reinitialize my range from the initial range to this new range, that would be from low to mid minus 1. That means if I find a time in this range in which I can produce T products, then I am gonna update my answer to that time, because I want the shortest time. Fine, so I am trying to shift to left side as much as I can. On the other hand, if these number of products are less than this T, we can't make our T products in this mid time, then that means I'm standing on this bad side of the timings. So there is no use to stay here, we'll have to shift to the right side. So the search space in that case will be reduced to mid plus 1 to high, because we'll find our answer in this range, we'll find our valid time in this range. So in this fashion, I will have my answer stored in this variable, which I will be returning from the function. So that's how this algorithm works. Let's see the implementation of the ideas which I explained here. So this is the shortest time function which takes in the number of machines we have, the number of products which I want to make, and this nums array represents the array containing timings for each of the n machines to create a single product. So I initialize my boundaries low to 0, high to 10 raised to the power 18, and answer variable initialized to 0. Fine. Now let's run the usual binary search while low is less than greater than high. Calculate the middle element using this formula. Initialize a variable sum to 0. Now iterate over all the machines and count the number of products which each machine can make in these mid seconds, which is calculated by this formula, and add those number of products into this sum. So this basically represents the number of products which I can create in mid seconds. So here's the condition that, let's say at some point while I'm traversing the machines, I exceed the number of products. That means I have already created the products which I required. I don't have to use other machines. So there is no use to iterate for the rest of the product. So I break right here. Finally, after I have computed the number of products which I can create, I'll have to check if the products which can be created in this mid seconds are greater than or equals to the demand. If they are, then that means yes, it is a valid answer, but there is a scope for a better answer. So reinitialize the boundaries to low to mid minus 1. This is the new search space where I want to look for my answer, because I want to find the minimum time. I want to minimize this answer. Otherwise, if this is not the case, I can't make my T products in this sum time, then reinitialize the boundaries to this mid plus 1 to high. Fine, because I will find my first time where I can create these T products in this range. Fine, so this is usual binary search. I hope you are familiar with this strategy. Till now you don't have to think much about it. Let's see. Okay, so at the end of this function I return the answer. Fine, so very easy. If you have followed this playlist, you must be able to solve this problem very easily. Fine, so that's the that's all. We don't have to create any. You can put this code into a function. Let's call it is valid function or check function, like the boolean function, and you can check if the particular mid is valid or not. Fine, so let's say in the next, so let's discuss the time and space complex search here. This is binary search. This is gonna take log n. Okay, so this capital N is not same as this n. This basically represents the length of the range that we have. Okay, while for each iteration, for each of these log n operations, we have to iterate over the array in the worst case. So that is contributing another factor of small n. So this is the time complexity, big O of n multiplied by log n, while the space complexity is constant because I am not using any auxiliary data structure here. Okay, so this is the time complexity and this is the space complexity. Let's jump to the code implementation part. Okay, so this is a solution class. Let's create the function shortest time, which takes in the number of machines we have, the number of products which I want to create, and the timings array, which represents the timings of each machine. Let's initialize our boundaries low to 0 and high to 10 raised to the power 10 raised to the power 18, 1e 18, and an answer variable to 0. Let's iterate over the range. So let's perform the binary search over this range low to high, calculate the mid element. Okay, since this number exceeds the capacity for this int variable to hold it, this is wrong to use int here. I will have to use long. Okay, so I will replace this int with long. Answer with long. Fine, so let's find the middle element, low plus high minus low divided by 2. Now initialize a sum variable, iterate over it, iterate over all the machines, and find the number of products. Okay, so let's call it number of products. Okay, now which is calculated using like mid divided by num size, and if this is the case, then I have to, okay, so like at any point, let's say if the number of products that I have exceeds the required products, if this is the case, then break right here. I don't have to use the products generated by rest of the machines. So when I break out of the loop, let's check the number of products which I have. If these products are greater than the required products, then this can be my answer. This mid can be my answer. While let's check for the very first timing in the left range, that is initialized to mid plus 1. Finally, at the end, I will have my answer, which I will return right at the end of this function. Okay, so very simple implementation, just binary search over the answer. And this is the implementation in C++. Let's see the implementation in other languages. Okay, so this is the implementation in Java, and this is the implementation in Python language. That's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel, and keep following this binary search series for more such problems. We'll be discussing hard problems as well. So that's all, and I hope to see you all in my next video.